Hello everybody. We are due for another video, and I'm not changing topics on this video. I'm going to continue what we were talking about in the last one, which was graphs of statistical data. Okay, now before I show you, I think it's good to think of where we are with this and what the reason is we do it. And when we engage in statistics, we start with raw data most of the time, which is unorganized, unsorted numbers. Okay, and our job is to sort through them and make sense of them so that people can, visualize it and as a result see patterns and draw conclusions, right? That'd be our ultimate goal. Okay, now, all right, the StatCat's going to make an entrance here. And StatCat says, so far, well, let's see, what have we done? Histograms, yeah, we did that, I think in the last video. Frequency polygons and the ogive. So all those I think we did in the last video. So for this one, we'll learn about stem and leaf plots, pie charts, and scatter plots. And that'll cover just about all the different graphs there are for raw data, okay? Now, let's start with the stem and leaf plot. The stem and leaf plot is something that to me looks very strange the first time you see it, okay? But it's, I think, simpler than anything we covered in the last video. But let's talk about it like this. So example for the stem and leaf plot. Suppose that these are the scores on a biology midterm exam, okay? So this is the raw data. It's unsorted. The numbers appear random, okay? Now, I actually got this problem off of the MyMathLab homework, and when I was looking at this problem on the homework, I used StatCrunch, and I know I made a video about that, but that's one of the add-ons in MyMathLab that will allow you to sort the data, so this is a little bit easier to look at and do whatever you need to do with it, all right? So I used StatCrunch, and I sorted it in ascending order because, at least me, when I make a stem and leaf plot, I think it's best to see the numbers lowest to highest. Okay, so that's what StatCrunch allowed me to do. Now, this is the raw data, okay, unsorted, random numbers, and this is a stem and leaf plot. And like I said, to me, it looks pretty weird the first time you see it. You see these numbers here, that's called the stem, and these other numbers over here, that's called the leaf. This vertical line through the middle, and that's supposed to somehow organize this. All right, let's talk about how. So in every stem and leaf plot, you would include a key. Okay, so the key for this one says 6 bar 7 means the number 67, or think of it, 6 vertical line 7 is 67. And that does kind of look like what we got going here. We got these numbers and a vertical bar and then some other ones. So let's look at this row in particular. Here's what 7 vertical line 5, 5, 5, 6 means. That represents the fact that there are scores in the raw data of 75, 75, 75, and 76. See? 75, 75, 75, and then 76. And sure enough, there's 3 75s, okay? And then 176 among numbers that are in the 70s. So you can think of this as 60s, 70s, 80s, 90s. The 9 and the 0 means there's a 90. The 9 and the 1 3 times mean there's 3 91s, and so on, okay? So that's what a stem and leaf plot is. And well, does this accomplish my original goal of being able to visualize the data and see patterns or draw conclusions from it? Yeah, I think so. I mean, it looks like not very many people at all scored in the 60s. Yeah, at a glance, it might be kind of hard to see that if you just look at this quickly, the raw data. But, only 2 people scored in the 60s. It looks like most people scored in the 80s or 90s, or I could say even that the scores are skewed towards the 80s or 90s, okay? So yeah, I think stem and leaf plot is, one of many ways, one of many types of visualizations or graphs where we can see the overall pattern in the raw data. Compare it, that's the raw data, look at that, versus the stem and leaf plot. Yeah, I can see a lot more in the stem and leaf plot. But these numbers are the same as these. They're just organized and they're just visualized, okay? All right, so that's what a stem and leaf plot is, and that's how you make one. Oh, I can't emphasize enough, like they all would have to have a key of some kind, where like the digit here, vertical bar digit there, translates into a number, okay? Whether that number is a big number or a small number or a number with a decimal in it, you can always interpret and make your stem and leaf plot from the key, okay? So next thing was something that I think at least first appearances would look a lot simpler than maybe anything that we've talked about so far, and that's a pie chart, okay? So, all right, what's the stat cat have to say? The pie charts look simple, they really do. But if you were going to make one from scratch yourself, or if you saw one and you thought something didn't look right about it, you know, you thought something seems off here, then there are some technical details and some math about pie charts that we should all learn if we're going to learn statistics, okay? So yeah, pie charts look simple. Here's a simple pie chart, okay? Now, most of the time when I make the videos and I include examples, I get my data from some other source, either a textbook or MyMathLab or sometimes the internet, whatever. This I did completely make up because I wanted to make a point about pie charts. All right, so let's imagine here's a make-believe survey I did. 20 people were asked what they liked about summer, and let's say they were just given two choices, okay? So what do you like best about summer? Is it the beach or is it that you get time off from school? So we asked 20 people that. And the results are in the table, okay? So 15 people said they liked the beach the best, and 5 people said they liked that they got time off from school. And maybe not many people would, if you're going to finish a college degree, it's hard to take the summer off, all right? But anyway, so let's say that those are the numbers. This would be the pie chart, okay? All right. And the pie chart has to reflect the actual proportions of the raw data. So, in other words, like you look at this raw data, and there's a total of 20 people, right? 15 and 5. So it's just like I said up here. Well, what portion of the chart should the beach be? Like, what's 15 out of 20? So if you get your calculator to take 15 out of 20, all right, that turns out to be 75%. All right, when you divide 15 by 20, you'll get a decimal, 0.75, which is interpreted as 75%. So when I make this pie chart and I put the beach on it, it better be 75% of the chart. So look, there's like a circle, and it's divided into, you imagine, quarters. And this is 1, 2, 3/4 of it. 75% is 3/4. That's 75% of the chart. And then this other one, well, this would be the other 25%. But, here, if you say, well, 5 people, 5 out of 20. All right, so 5 out of 20. So if I do that, that turns out to be 25%. If I take my calculator, I divide 5 by 20, it'll give me 0.25, which is 25%. All right. Now, we need to know the numbers. Here's why. Like, sometimes when people do statistics or present you with statistics, they sometimes give you inaccurate information as if to persuade you of something to their benefit, all right? So yes, you can lie and you can mislead with statistics. It's not always an exact science, as they say. So let's see, here's what the StatCat says this time. It says, could this pie chart possibly be correct for that data? Okay? So here's the data. 15 out of 20 prefer the beach about summer, and 5 out of 20 prefer that they get time off from school. Why couldn't this be right? The way this chart split, it's like half and half. This is almost half of the chart, time off from school, and this is almost a little bit more than half, the beach. Well, those just aren't the amounts in the raw data. Okay, so when you make a pie chart, the part of the pie that you represent to any category has to be an accurate percentage of what those numbers were to start with, okay? All right, so this one's correct, 1/4 and 3/4. And this one is not even close, all right? Now I'm drawing this by hand, like maybe I'm only going to get it close, but this one's not even close. All right, so let's talk about this. If we're going to make a pie chart, or if we're going to recognize whether one is actually accurate, then we need to know a little bit about angles. So let's take a break real quick and let's talk about angles. So like this corner right here is a 90-degree angle, okay? And then this rotation from this line to this line, that's 120 degrees, okay? Now, like, maybe you could expand a little bit. What if I went like 90 and then another 90? That'd be 180 degrees. So that'd be like this. So like if I rotate, say I start here and I rotate over to there, that's 180 degrees, okay? So yeah, I'm gonna say if I started here and I go 90 and another 90, that's 180. So angles work something like that. We won't go into a huge discussion about it, but we'll probably learn just enough to understand the pie charts, okay? Now, well, let's do, how do you measure angle? Here's a protractor. This is how you measure angles. So for example, if I was gonna show you an accurately measured 65-degree angle, well, all angles start with a line. Okay, so here's my starting point, okay? And then notice if I put that point on this hole, then there are these numbers, 10, 20, 30, 40. So those are the angles. So there's 60. So 65 would be right in the middle. So if I draw a line up to that mark I made, then that would be 65 degrees. Okay, so this is what a 65-degree angle looks like. Now that's a little bit of a crash course with angles, but right, we're not doing a whole geometry class. We're doing enough to learn pie charts. But yeah, I can use this to make any angles between 0, and then if I rotate all the way over here, I get 180, okay? Now, if it's angles or something you're having trouble with and they're keeping you from getting the pie chart questions right, then just let me know. We can talk more about it. Now let's do an example, okay? All right, so say you get the raw data on MyMathLab. How can you build or recognize if a pie chart is correct, okay? So let's say that 1,000 employees were asked about their reasons for their most recent missed workday. And the categories fell into vacation, family obligations, illness, or just non-vacation leisure. They just want to take the day off, maybe, okay? And then here are the responses. And they add to 1,000. All right, there's 1,000 people. Everybody gave an answer, let's say. Now, so far, there's nothing controversial about that. These were just the answers that the people gave. All right, we can't argue about that. But I need the percentages. You know, if 146 out of 1,000 people said that vacation was the reason, what percent of the whole is that? Because I need to know that number, because I've got that part, that answer has to occupy that percent of the pie chart, all right? So here's how you figure the percent. 146 out of 1,000 total. If you divide that, you'll get 0.146, okay? All right, so there's your percentage. Now, 0.146 would be 14.6%. And for the sake of drawing or looking at a pie chart, you could say 15% or something like that, all right? Now, if you want to look at the angle, like if we're having to actually measure or build a pie chart ourselves, like we want to make sure the angle is correct, you know, I mean, what is 14.6% of a pie chart? What's that look like? Well, the whole circle is 360 degrees. So if this answer or category is 14.6% of the whole circle, to figure the angle, we do 0.146 times 360. 360 degrees. That's 52.6 degrees. That means that this category should be 52.6 degrees on the chart. So you figure the percentage, which is the number divided by the total. you'll get a decimal, in this case 0.146. Take that, multiply by 360 degrees, and that's the angle on the chart. So the vacation section must be about 53 degrees, okay? I can't draw a 52.6 degree angle on paper, but I could draw like 53 is close enough, all right? Now, same thing with the others. We figured the percents and the angles the same way, exactly like the first one. Now, whenever I drew this earlier, and I got my shading pencils out and everything, then I used the protractor because I want to make it for the video, and I want it to be, all the measurements to be accurate. Then, yeah, vacation, that's 14.6 degrees. This wedge right here, that angle, sure enough, I measured it to be about 53 degrees, okay? And then normally what we do is we go from least to greatest. So illness, okay, which was about 23%. 0.225 is about 23% with some rounding. So 22.5% is okay to round it to 23%. That one was 81 degrees. So I measured this wedge, this angle to be 81. And then leisure and family came in at 30 and 33%. Okay. All right. And I measured the angles the same way between those two. Okay. So that's a finished pie chart. Now, if, say, on MyMathLab, maybe it gives you several different options for which pie chart is correct for the data, it would come down to, are the sections the right percentage of the whole circle or the right angles? Okay. All right. So that's how we think about pie charts. Last thing is a scatter plot. Okay. And this is one that we'll make a lot of use of later on in the class. But right now we'll get the basics of it. So scatter plots, what's the stat cat have to say? So we use scatter plots to discover trends in paired data. Now I won't tell you what paired data is, I'll show you, all right? It's a little hard to explain, but it's easy to show you. So here's an example of some paired data. Paired means like, you'd almost get the feeling, well, it makes sense for these two things to go together. They're paired together. So in this case, the data is the hours spent studying for a test and the grade that the student received on a test. So every student will say spent a certain number of hours studying for a test and got a certain grade. It makes sense that those two things go together. I mean, don't you think that normally anyway, that the amount of time you spent studying for a test has something to do with the grade? Okay. That's what I mean by paired data. Now, let's say like, here's our paired data for a selection of students in a class. Okay. So this student here studied 0.5 hours, half of an hour, and got a 40. And this student studied 0.75 hours, which would be 45 minutes, and got a 60. Okay. Now, all right, and then there's the rest of it. The student studied 3 hours, got an 80. This student also studied 3 hours, but got 90, right? Every might be a little bit different. I'm not expecting these numbers to be clean and predictable, all right? I would expect there to be a trend. I do think that most of the time in general, the more hours you spend studying for a test, then the better your grade is. That's why people study for tests. All right. Now, in a scatter plot, here's what we do. One of the variables, such as study time in this case, goes on the horizontal axis, and the other one goes on the vertical axis. And we just put a dot for every one of them. Like, you see this dot right here? That represents studying, well, here's 1 hour, 0.75 hours, so it's just before the 1, and 80 for the grade. It's at the 80. So that's what that dot represents. It's this data point right here. The student who spent 0.75 hours studying and got an 80 for a grade. That dot right there. Now, I put all the dots on there. There is like a sort of an upward trend. So here I got my red pencil and I vaguely outline that. And I see, well, you see how the dots kind of go up and to the right? That means that, yeah, the more, in general, the more time you spend studying, then the better your grade is. Now, is it true that every dot or every student or every data point is part of that trend? Well, this one's not, I would say. Like this person actually did really well, but didn't study that much. And then this one is not part of the trend either. This person studied like a decent amount, 2 hours, but got a really bad grade. Okay, they got a 30. So those are called outliers. And if you hear of medical studies, just casually, maybe even if you read the news or anything like that, you might hear the word outlier occasionally. And what that means is if there's a trend between two variables, but then there are these data points that don't match the trend, then those are known as outliers. Okay. Now, the fact that what we see here is that the more time you spend studying, in general, the higher your grade is. That's called a positive linear relationship. It just means that as one variable goes up, so does the other one. Okay. All right. Well, let's talk a little bit more about the trends and the types of graphs you might see, because I don't think it's that hard to make a scatter plot as it is. Okay. So what's the stat cat have to say? Let me see here. So, well, okay, among all your options, paired data, which is the kind of thing you see in the scatter plot, variables that make sense to go together, can be positively related. That means that if one of them goes up, so does the other. That's like the example we just saw. The more you study, generally the higher your grade. They can be negatively related, and that means if one goes up, the other goes down. So an example of that, like a real life example with people, normally the hours you sleep per night versus your age. Well, normally as you get older, you sleep less at night. Like newborn babies might sleep 17 hours a day, and people over 65 on average might sleep, I don't know, like 6 to 7 hours or something like that, and there are outliers, there are exceptions, but in general, the greater your age, the fewer hours of sleep per night you get naturally. Okay. So that would be a negative relation. That'd be like this. Like if we put age here on the horizontal and hours of sleep per night on the vertical, yeah, then the bigger this number got, then the smaller this other number got. Okay. So that's a negative relationship. Or they might not be related at all. Maybe even variables that you would expect to be related don't have any relationship. Okay. So I can't remember where I got this data. Oh, it was from the textbook. Okay. So here's the data and the concept this time. What is the relationship between the number of students per teacher, say at a school? Maybe there's like an average number or something like that, but every teacher is responsible for a classroom of a certain size, and the average teacher salary. I would think those two things would be related. That the bigger your class size is, the more students you're responsible for, the more grading you have to do, the more work it is in general, that your salary might be higher. That's what I would expect. But let's see. So here's the data. So on the X or horizontal axis, we'll have students per teacher. Okay, like 12.6 students in a class, 14 students in a class, so on and so forth. 19 students in a class, 19.3 versus the average salary. Okay, so this is in thousands per year, 42,000 per year, 50,000 per year, 38,000 per year, so on. Okay, so okay, that's the raw data. It's not organized. I'm just looking at it. I just see a bunch of numbers. But I'll make the scatter plot in the same way. On the vertical axis is the salary, and on the horizontal is the students per teacher, or the class size. And I just plotted the numbers, okay? Like, 12.6 and 42.4, that's this one right here. So I went over a little bit more than 12, and I went up a little bit more than 40, okay? Now, it's like, I don't think it kind of looks a little bit like things go down. That the more students that you're responsible for, the less you got paid. But it's not like they're in a tight line, okay? Now, this is a little bit, unfortunately, a matter of an opinion, but something like that's negative or positive will look like this. Will there be like more or less a line that you can match it to, all right? And this just kind of looks like, look how many dots are outside of the line. Look how many outliers there are, okay? So I would say about this one, there's not a relationship. Like going into the problem, I would expect these things to be related. I would expect as this goes up, I would expect that to go up too. But then I put on a scatter plot, I don't see it, all right? It doesn't look like there's a relationship at all. And if there is one, it's definitely not what I expected, okay? So anyway, that's all three types. So we did, what was it? Pie charts, stem and leaf plots, and then the scatter plot. And this one we'll make a lot of use of later. We might even try to figure out what the line is. Like if the data is paired, is there an equation that more or less predicts the data? That's something that we might do later on. And because paired data is so common, because it's such a common thing to see how variables are related to each other and how one thing affects another, then at some point we'll do way more with scatter plots and similar data.